Welcome to session 3 of the Intro to AI-Driven Science on Supercomputers. For those of you who don't know me, my name is Paige Kinsley. I'm the Education Outreach Lead here at Argonne, here at the Argonne Leadership Computing Facility at Argonne National Labs. To get started today, we're first actually going to go back over something that you've already seen, because today we're going to ask you to actually get on our machine. So we're going to remind you on how to do that. And from there, Tanwi Mallick will come and talk to us about neural networks, specifically using Tensorflow as a tool. And then we'll also hear a science talk from Jiali Wang on AI in climate science. So before we jump into the tutorial itself, I'm going to hand it over to Taylor Childers, and he's going to talk to us about Jupyter Hub on Theta.
Thank you, Paige. I'm going to share my screen. Okay, so I just wanted to quickly remind you guys, so we have been using Google Colab. If you are comfortable with that, you can continue using that for today's session. I think after next week's, you really have to switch to using ALCF systems. So make sure you've got your accounts in order, that you can log in via the command line using SSH. But for today, if you are interested in using ALCF systems, you can go into the introduction in our GitHub repo. One of the things you might want to do on a weekly basis is, if you have forked our repo, you might want to run this command where you are synchronizing your fork with the upstream mainline repo. So I just wanted to point that out. That's on the GitHub homework README file. And then there are instructions for hopping on our Jupyter server in here as well. And I'll just walk you through that real quick. So if you go to jupyter.alcf.knl.gov, you'll come to this login page. We'll be using Theta GPU. So I'm going to type in my credentials here and log in. I have my phone two-factor authentication app, the Mobile Pass. Otherwise, you can use your keychain two-factor authentication plus your PIN code. Okay. So if I chose local host, I would actually be using the login nodes of Theta GPU. So those are not the GPU enabled nodes. We want Theta GPU compute nodes. And I'm going to choose the single GPU queue. And I'm going to use the ALCF AITP, so AI tutorial program. And you can set this between 5 minutes and an hour, so 5 to 60. And you can click start. So that submits a job to the queue on Theta GPU, the single GPU queue, and says, I want a GPU that I can run Jupyter on. And you can see that we're pending in the queue. And once it's ready to start, or once we actually have the GPU instance, this will change from your server starting up to a directory listing of your home. Hopefully this won't take very long. There we go. So I have the GPU, it's starting up the server. It's giving me the my home directory listing. So this is all the stuff that's in my home directory. Your home directory will look different. But I have checked out the AI for Science training series. And so I can click on that, and then it's going to show me the contents. And from there, I can navigate to a notebook that I am interested in seeing. These are the ones that you saw before that I presented in the first session about linear regression. And so now you can see your notebook, and it operates very much like Colab, where you can hit Control Enter, and it will execute your code. Actually, I may need to choose a kernel here just to make sure. That's right, yeah, because right here you can see it's using the generic Python 3 kernel. We want to make sure we're using the Conda with the latest date kernel on here, just to make sure we're using the latest versions of our AI libraries. And from there, we should be able to run these. Yep. And so you can see once it has the number here, it's spitting out information, making plots, that our kernel is working properly. The other thing to be aware of is being thoughtful about how we take care of these. So if I just close this window and I leave, that doesn't actually stop my job on Theta GPU. You will continue, if you were running in your allocation, for instance, if you had an actual allocation on ALCF systems, you would continue to get charged for that time. And you would be blocking other people from using it. So it's useful to go to the control panel. Yes, I want to leave, and stop your server. And at that point, you can log out and you're done. Okay. So with that, I will pass it over to Tanwi, who's going to be presenting AI using the frameworks.
Yes. So, hi everyone, I'm Tanwi Mallick, and I'm going to talk about the AI frameworks using TensorFlow keras. Let me share my screen. Hopefully you can see my screen, right?
Yes.
Okay, so here today's tutorial is here, like 3 neural network TensorFlows. If you open this one, you will get this 2 notebooks, and I'll be going from this one first. So for this tutorial, what we have seen last week is that we built the neural network from scratch using Python only. Now this time we'll be building this similar kind of neural network, but instead of using Python, we're using TensorFlow keras package, and we'll see how this makes easier to implement the networks and other things. So for that, today we'll be using CIFAR10 dataset. Here is the description of the dataset. So in this dataset, we are having 10 different classes. So you can see here in this images. So these are aeroplane, automobile, birds, cats, so on and so forth. And each of these images are basically 32 cross 32 dimensions. These are color images, so it has 3 channel RGB. I'm going to show you how this channel looks like. So for that, first let me import this packages, and then now you can download the dataset from using TensorFlow Keras dataset for .c10 data download. And if that doesn't work, then you can download using this. So wget, and using wget, you can directly download the dataset from this link, and then enter this dataset. It will be in your local drive. So let me do it in this way. So I have loaded the dataset, and it's showing that the C10 dataset loaded, and it has trained dataset of 50K images and test dataset of 10K images. And if you see the size of the dataset, you will be able to see that is 32 cross 32 and 3. This is for the third dimension, and this is Y-train. This has the label for each of this dataset. So if you can download in this way, you can skip this. And if so here you can see that here is the example. Here I'm showing, for example, is the horse image. This is a color image, and for this image, computer basically represent this image as a grid of 2 by 2 pixels, and each pixel has the intensity. Each pixel has the intensity of that particular position. So, as it is a color image, it has 3 channels, that is RGB. So first one is R, that is red and green and blue, and so this all are 2 by 2 metrics. That is how it is stored in the computer, and that's why the size here is, if you see, the size here is 3. That is, for each images we are having 32 plus 32, 3 grids of 32 plus 32 images. And so now we are interested in classification problem using this data set, and we want to build a linear model for that using Keras libraries. So whatever you have done in the earlier tutorial using Python's library, we will be trying to use Keras library instead of Python. And here, for doing that, we first flatten our image into a vector. So we are not using the structure, we are converting to a vector, and then our dense layer is used here. Here you can see in the code, and this is the dense layer, and this is basically the function x w plus b here. So x is the input, w is the weight, and b is the bias, and some activation function can be applied on it. So and at the end, it will do the classification into 10 image classes. So it is the number of neuron in the dense layer is 10, and the softmax function is basically giving us the probability distribution in each of these classes, and the max probability will be the actual class for that image. So here, that is how we define the first layer here. And for the input here, you can see that the input is getting flattened, and that is now this is the input to this layer. Next will be, so this is how we define this model. Next is that we are calling the linear model and calling the compile function using the sparse categorical cross entropy. Here we are not converting the levels in one hot encoding, so that's why we are using sparse categorical cross entropy loss function, and optimizer is stochastic gradient descent, and we are measuring the accuracy here as a metric.
Tanwi, I have a question. So we don't see any compile function inside linear classifier.
Really?
How are you? So you are calling compile function
Okay.
from linear classifier.
So actually it's inheriting this Keras model. So we don't need to define that, but as it is inheriting this Keras model, so it's there already in the base class.
Sounds good.
So if you do the compilation here, so you can run the cell. Okay, sorry, I didn't run the previous one. Now, so here I use stochastic gradient descent here. You can see what are the different option of optimizer listed here by clicking this link. Now, now we are trying to, we defined our model. Now we want to fit the data and learn the model. Okay. So here we are defining this thing. First is the batch size and the epoch. So epoch means one pass through the whole data. So that means our entire set will pass through the model in one epoch. And now how we are passing the data, that's using batch size. So suppose we are having 100 images, and then we are defining batch size as 10. Then we'll be taking 10 images at a time and pass through the network. So there will be 10 total iteration to complete one epoch. So we'll be passing 10 data at a time, and 10 times we'll do the same thing to pass 100 of our sample, and that is how we'll be completing one epoch. Okay, so here we are defining the batch size as 512 and an epoch as 30, and then we are fitting this linear model with our training data. So this is the training data, this is the level of those training data, and here we are dividing the batch size and epochs. Now let's start the epoch. So here you can see that as it is training, accuracy is increasing and loss is going down. It will do up to 30 epochs. And now here, if you use large batch size like this, it will take large amount of data at a time. But if the batch size is too large, then it will take the almost of your entire data set, and then we will lose the generalization capability of your model, but your training will be really fast. Or at the same time, if you take too small batch size, then it's going to be then it's going to take large time to finish one epoch. So you have to choose something in between. Is one of a hyperparameter which should be tuned based on your data set and model to get best performance out of your neural network. Now I think the training has completed. So you can see the accuracy increased and the loss decreased here. So the nice thing is that we don't have to write all the training loop and other thing. We just use Keras model and just call the fit function and fit the data and it train. So it's really easy, right? Now, if you do the model summary, then you'll be able to see the number of parameters for this. So here in the summary, you can see how this number of parameters is coming. So we have So that was the image size, and that was the number of layer, and then the number of neuron in the dense layer, and plus one bias vector, that is the total number of parameter here. So here we are visualizing how the training loss is going down and accuracy increasing loss. So here the basically you can see that we did that plot. So minimizing the loss function during training should increase, should decrease over time. And here you can see this, how the loss is decreasing, and at the same time accuracy should increase over time, and it did in this way. So now now we trained our network. Okay, now let's do some inferencing using the network and see what is the test accuracy for our given data set. So here we are calling the evaluate function, and we are basically giving the test data and test level for this, and calculating the accuracy. So here you can see that for our simplest model, simplest neural network model, the accuracy is like 39.36%. So basically this neural network has only one layer, one dense layer, so accuracy is not very good, but there are ways that you can improve the accuracy also. Now let's take a closure look where the neural network fails. So here we can see the failure, and basically here this is the function I'm using to show the failure, and this here we are predicting using y-test. And now visualizing those images where the test label is not matching with the prediction. For example, here the actual level is 9 and the prediction is the prediction is 9 and the actual level is 8. So here there is a mismatch. Similarly, all the images are misclassified in this network. So that was a single layer perceptron. Now we can build multi-layer perceptron with more complex multi-layer perceptron with nonlinear activation function and dropout layers. So here here this is the first layer, similarly dense network with 50 neuron, and here we are choosing the activation function ReLU. And after that, these are commented, so you can add as many layers you want. Let me comment it. So here the second layer, here the second layer is adding another dense layer with 50 neurons in it with the activation of activation function ReLU, and then we are introducing a dropout layer. So this layer is basically dropping out neurons in betweens in each training phases in each epoch, and and that reduces the overfitting also, because it's arbitrarily dropping out neurons in between. And after that, we are adding another dense layer with with 50 neurons and same dropout function. And finally, we are coming to the dense layer with 10 neuron as the number of output classes with softmax function. So that's basically is giving us the probability distribution of each of these classes. So this is a more complex network compared to earlier one. We have increased the number of dense layer and introduced dropout. Okay, and here basically we are flattening the input and giving this to our first input layer, and then the output of this input layer is giving to the next layer, and then the next one, so on and so forth. So basically here also we are making a fully connected layer, but with more number of layer, and we are flattening the image and giving it as input. So now we'll be seeing the performance of this architecture in this neural network. But one point I want to mention here is that here we are providing in both of this network, we are flattening the image. So basically here, we are not considering the spatial features of the images, like how the shapes and other things are forming here, spatial connectivity between pixels in the 2D grid that we are missing here. We are making a flat 1D vector out of it, and providing that as an input in our network. So we are losing that information. So that's very important, because eventually we don't want to do that, and we want to find a better neural network for doing image classification kind of task. So that I'll be talking in my next notebook, but for this time being we are not doing that, so we are flattening on the input. And now let's compile. Now let's call this nonlinear classifier, and then compile it with the same loss function and optimizer. Okay, let me do it first. So I compiled, and next I'll be running that in the similar way, where I define the batch size, define the epoch, and then fitting the training data and training level with the defined batch size and epoch. Let's run this. So it will be running for 30 epochs. The accuracy is going up and loss is going down. Now it's finished. So let's see how the loss function is behaving. So here also you can see with the more number of epochs, loss is going down. That means the network is learning and the accuracy is going up. So it's good in that way. Now let's do some inferencing and see what is the accuracy here. Yeah. So yeah, the accuracy increased a very little, like 40.22%. So it's not a very big jump. And if you see some of, you can here also visualize some of the misclassifications here. So these are the failure where the images got misclassified into another class. So now you can see, like, now you can see what are the classes where the misclassification happen in most of the time by doing this, by computing this confusion matrix? Here in the confusion matrix, as it's 10 cross 10 matrix, and you can see like this is the, for example, first class, how many times this class has been classified as this class. So this is the class 0 is classified 458 times as class 0, but it also classified as class 1 this many time and this many time as class 2. So that is how you can read the confusion matrix. And here for classification accuracy per class. So here you can see that for each of this classes, what is the accuracy of the classification? What is the classification accuracy? So for class 0, the accuracy is like 45, and class 1 is 53%. But here for class 3, the accuracy is very low. So that is how you can visualize what is the classification accuracy per class. So here now we'll be doing an in-class exercise to improve the accuracy of this model. So here just I want to mention a few things, that what we can do here is that we can vary the different hyperparameters, such as the learning rate. So I showed you the learning rate is too high, and that's why the model is training very fast. So this learning rate can be changed, and the number of epochs the model can learn for more time. And then along with that, you can change the, you can do some experiment with a different optimizer like SGD. So some of the optimizers are listed here. Different options are given here. So these are a few things by which you can improve the accuracy, but at the same time, I also want to mention is that here we are flattening the images, which we shouldn't do, because that is how we are losing several information from the images. But this is the also this is the simplest neural network for the image classification. In the next notebook, we'll be learning about convolution neural network, which is more appropriate for image classification because it takes care of the inherent features present in the images that helps us to capture those features. So yeah. So with that, we can go to the breakout room and see how can we improve the model accuracy.
All right, so I'm gonna throw you into breakout rooms. Hopefully you can work on things together with other folks. Tanwi, how long do you want them in the breakout rooms?
So we have, I guess we have 20 minutes time, right?
We've got 15 minutes before break.
Okay, then yeah, we can go for 15 minutes.
15 minutes, okay. So we're gonna put you in the breakout rooms for 15 minutes. Folks from ALCF will come around and try to answer questions as you have them, and then we'll go from there. All right, welcome back, everyone. I'm gonna have you come back from break, and we're going to dive into a science talk by a scientist here at Argonne. So I'm going to introduce Jiali Wang. So Jiali is going to talk to us today about using AI applications in climate sciences specifically. Jiali is an atmospheric scientist in the environmental sciences division here at Argonne. And I'm going to turn it over to her and sort of go from there. So Jiali, if you will.
Yes, thank you, Paige.
Of course.
I'm looking at, is this
Current looks like we're currently seeing your internet. It says Zoom for Government right now.
yeah, I think I just shared a run slide, but this time it's right. Okay. Hello everyone. And
oh, it looks like we're still not seeing it.
Okay. It's on the sharing mode.
I would stop share, redo, make sure everything gets squared away. Okay. Sometimes it
okay,
can be funny.
Right now, maybe this one.
Wonderful. Okay, good to go.
Okay, here you go. My name is Jiali Wang from Environmental Science Division, and I'm an atmospheric scientist by training, but I do regional climate modeling for extreme and risk assessment. At TVS, we do many things as you can see from the pictures, right? Measurement about the weather and ecology, agriculture, and even many other things. If you're interested to join us in summers for projects, and today we are talking about the AI applications to climate science, and in particular, I'll give a couple of examples about how we can use AI or machine learning in the climate modeling area. And why do we think about AI? And it's not only because we're told to think about this, but more importantly, it can be very powerful in terms of helping the climate simulations, understanding uncertainties, and even detect unknown physics or dynamics. And one of the reasons we're looking at is, as you know, doing learning using AI would require not a lot of data set. And we have more and more data generated by either observations, satellite detections, instrument measurement, and we also have simulations from different climate models at global scale, regional scale, at different resolutions. And those data are getting bigger and bigger. And we can take advantage of all those data sets to develop something that can benefit our climate models, which can improve their performance so we can get a high confidence about future projections. And that's one thing. We have a lot of data now. The other thing is developing a physical process for Earth system model will take a long time. And as you can see on the lower left figure, there are very sophisticated processes in the Earth system model that describing everything in the atmosphere or outside of your window. You can see that clouds, soil, land surface, but below the land, hydrology, everything. And all those processes actually need approximation to describe the physics, and developing those would take a lot of time. Even we have developed such models, and there are dozens of models that are developed by different institutes, different countries at different resolutions or different accuracy. and using the state-of-the-art climate models, as we can see, if we would like to simulate such a large domain, covers North America, simulate 1 year of data will take about even more than 2 weeks to reach a spatial resolution at 4 kilometers, which is about 3+ miles. And this will require 300,000 CPU hours. And this will take forever if we think about like doing this on our laptop. And such models would include lots of physics processes, and some of them can be very expensive. Example on the right shows you that the radiative transfer describing the long wave and short wave radiation take the most time in those climate simulations. And the second would be the microphysics, which describe the process of the clouds. And there are also processes describe the precipitation process, and all those take lots of time. Now think about if you can develop something using the AI, which can replace those big chunk of time, and that will reduce, right, in total almost more than 70% of the computation time. With that time, we can go even higher resolution to reach your backyard, right? And we can do lots of ensemble simulations by perturbating different processes. Then we can understand the uncertainty of all those simulations. So you know how certain or uncertain for the future projections when we predict global warming. So with that motivation, I'm giving some examples. We just talk about AI emulators for surrogates, right, for the most expensive physics processes. And this will allow us to do a much faster simulation. In that sense, we will be able to do a lot of simulations to better quantify the uncertainties, because model is, at the end of the day, it's still an approximation. It still have lots of uncertainties from those physics, right? From initial conditions, from future greenhouse gas scenarios, and all those. And if we can conduct enough simulations, we can understand what is the range or uncertainties across different simulations. And we can also do higher resolutions by output very frequent data and at spatial resolution as well, to do some climate risk assessment. That's what we do a lot at our division, right? To provide the climate change risks at the neighborhood scale or infrastructure scale. And if, for example, if you have a tower or which is your critical infrastructure, and you want to know what would be the flooding level, right, due to hurricanes or storm surge from the ocean or from heavy precipitation, and how that going to affect your infrastructure. And that would need a very high resolution model simulation, which will take a lot of computing resource. And we also would like to emphasize the importance of the collaborations. So either we are a scientist in the domain, right? They can be environmental science, climate science, ecology, and hydrology, right? And all those have some common problems, but they also have their unique problems, which need some speed up or develop new models. On the other hand side, we would also need the skills and experts from the machine learning scientists, computing scientists, and who would have the technique that can take our data to tell some knowledge that through the machine learning that we may not even know before, or we know some of them, but we don't know the reasons, things like that. So the collaboration is very important when we try to apply such technology into the domain science. And we have some problems here that we have been working with machine learning experts, right? For example, this is one scheme that in the climate models describing the boundary layer, which is the about 2 kilometer and below, or I should say near surface 2 kilometer, this layer which affected by human activities a lot. So we call this we call this boundary layer. And there is a scheme or physics process particularly describing this process. So we want to see, okay, how whether machine learning can emulate this process if we give the input variable and see whether it can output the variable that at a certain accuracy. So what we try is, okay, if we dump all the data with multiple vertical layers into the learning algorithm, and the learning doesn't know how they are connected with each other at the vertical dimension, it will still give you results. But once we tell, okay, if you can add the connections between the surface and the upper layers, or the connections between the surface and every layers that are below, those are actually considered in real physics in the climate model. And we found that when we consider those connections in the vertical dimension, and those models are giving better results with less data set, actually. So this tells us the importance of embedding the physics into the learning process. And we also have other examples that generating data from low resolution to high resolution. And we realized that climate models could generate different images if you run it at a different resolution, because there are other factors when we run the model. It includes the time steps, terrain effect, and eventually when you look at the low resolution and the high resolution, they're not actually exactly like a image at different resolution. There can be some difference that not only the resolution, but also the magnitude or the patterns. And this would bring some challenges for the learning and would need expertise from the physics to advise the learning development. And I think that's what I have for the 10 minutes. And if you have any questions, I can take that and we can discuss from there.
Wonderful. Thank you so much, Jiali. I think folks are currently populating our Slack with questions, but I'll get started. I guess one question I have for you, which I think can be really, really hard, is understanding that like these are simulations, therefore there's uncertainty. And I feel like in climate science, in like the globe that we're in right now, where everything seems to be falling apart around us, climate-wise, like how do you have conversations with experimentalists or other people about like, these are uncertain models and they can still tell us something that's important, like moving forward?
Mm-hmm. Right. So we use those climate models, and those are Fortran code, and they're made up with multiple physics approximations, and those physics by themselves already have uncertainty. And why their approximation not accurate, because there are still many processes that people don't know, so those equations actually cannot incorporate those, right? And when we don't know those, we will just use a constant parameter, and that will introduce lots of uncertainty. And different physics developed by different institute or different group would assume different parameters, and that will give you the largest uncertainty actually. So when we run different models, and that is the number one uncertainty we would consider. And when you change a different set of parameter, you may get a different conclusion, right? And that's one thing. But the bottom line is we always evaluate our model output against the observations. And we would evaluate in different aspects, right? We would look at diurnal patterns, spatial patterns, seasonal patterns, and we know the model are able to get reasonable performance, capture all those variabilities, right? If it's not, then we need to tune those parameters, and sometimes we need to even develop new stuff to capture all those. And there are always certain biases that it could be systematic bias, and those are something we need to even develop more observations to understand what's going on there. It's just one part of uncertainty, and there are many more, right? Like when you go to future, no one will know how those future greenhouse gas and also the population is projected correctly or not, and how far they're relative to the real situations. And that's why when we run future projections, we would do a bunch of scenarios, assuming, okay, if we do right business as usual without doing anything, okay, the CO2 will increase constantly. If we do something to do this mitigation, then your CO2 level may stay stable by the mid-century. So usually we would run a range of simulations to give such uncertainty.
Awesome. So another question from Catherine. Catherine asks, could you talk a bit more about how you embed the physics into the models?
Right. So I think so the physics outside of the window, right? Those are well known, but there are always something that are not known yet. So there are basic equations, right? And we would write the code to put into the model, and there are different physics, and they need to talk to each other, and we need to make sure those coupling are correct. And those different part of physics are always validated and calibrated using observations. And before a model can be used by users, they would calibrate over certain locations, depends on, for example, is that like a US-based model or a European-based model, they would calibrate over different locations and tune the certain parameters and make sure it gives reasonable performance.
Wonderful. Another question from Alfred. When we use AI to save time on simulations, we assume that the simulations will not give us any surprises. We're just using AI to beat down the complexity. What happens if the simulations are full of surprises and we don't know what we will get?
Right. That's a good question. So basically, if we use AI to replace the very expensive simulations, you're basically using the model simulations as a ground truth, which is not necessarily true, right? If the model gives you garbage, then you're learning from the garbage, right? Again, like I said, when we use those model results for anything, providing data for AI learning, providing data for future projection, the first step is always extensive evaluations from different angles to make sure the data is making reasonable, giving reasonable results before you can use it for any other purpose. And by doing learning, we actually can, you have model simulations that's correct, but you also have a bunch of observations, as I said, right? And those, we can consider those as truths, although there are also uncertainty, right? So this learning actually can learn both model simulations and observations, and you can, in theory, you can use observation to improve your learning and improve your model simulations.
Sure. Okay, so I think we have time for one more question. Bernardo asks, out of curiosity, have you worked on predicting the location and strength of hurricanes, for example? It's
Sure.
quite apt, yeah.
Yes. So basically that would be how you can predict the track of hurricane, right? I personally don't do such learning for the hurricane, but I think there are studies that are trying to learn those cyclones in their tracks. And predicting the track, I mean, using the classic numerical modeling is already a challenge, right? And predicting their intensity actually is also challenging. And right now we are actually working on how to improve the model simulation result, not the learning yet, but improve the model by considering more process. For example, actually the right now the weather forecast we're seeing right now, it doesn't consider, for example, a dynamic condition of ocean or waves, right? Which can change the sea surface temperature and change your development or the intensity of those hurricanes. And eventually you may get a wrong intensity or track. So we're trying to actually develop such coupling between all those components, atmosphere, ocean, and waves, to generate accurate tracks and intensities. And then you can use those better data to develop learning.
Wonderful. Okay, well, thank you so much for coming and speaking to us, Jiali. This was very, very helpful and really, really interesting. With that, I think we'll pop back over to Tanwi and continue with the tutorial itself. So thank you again, Jiali.
Okay, thank you guys. Bye.
Hello everyone, let me share my screen again. Hopefully you can see my screen. So in the last tutorial, we talked about classification of C410 dataset using fully connected neural network. Here we'll be learning about convolutional neural network, or CNN. And for that, we have to do few similar steps like loading the dataset, importing the libraries. Let me load the dataset here. Now, if you remember earlier, that we had three-dimensional data set and we flattened it in a single vector. But here in CNN, we'll not be doing that. Instead of that, we'll be learning from the entire image, and we'll be learning the spatial dependence between the pixels and those related information directly from the images, from the 2D images. So here I'll talk about the few operations which are used for the convolution. Is first 2D convolution layer. So basically what it is, so if you see this image, so this is our input image, which is a grid of pixels, and here is one filter. What is this filter is basically applied on the 2D grid and calculate and do dot product with the image and return the result of the dot product of this filter location here in the feature map. And that and then the filter basically move to the next place by sliding, and then do this, perform the same operation and return the result here in the next feature. So basically what it is doing is that you can if you see this image, you'll see that this is the input image, this is the patch, and taken from the input image, and this is the filter or kernel. I'm doing the dot product and here is the result. So basically what it is doing is that this filter is basically taking the image and then looking for the features in the image. For example, if you wanna find the ages in the given image, then this filter will convolve with the image and try to highlight the locations where the ages are, and provide you the resultant image where you will be find the ages here. So this convolution operation is used in deep learning to extract the feature which are present in the image. So earlier in the image processing, people used to identify those images, for example, those sometimes called handcrafted images, handcrafted feature, like for which people used to get the those feature like ages extracted from the image and give those as an input to the machine learning model. But instead of that, here using convolution recurrent neural network, we are trying to extract those feature directly from the images using this operations. So here the thing is that we are not here only using one filter, but instead of that, here you can see like learn 32 and 64 filters respectively. And these filters are 3x3 window size. So we are basically learning multiple filters. So for example, if one filter is responsible to find the ages, another filter is maybe responsible to find the shapes and other features. So we are learning multiple filters, and initially this filters learn the lower level images like ages, and eventually it learned the higher level images, such as from ages to shape to structure kind of thing. So that's the beauty of the convolution layer. Next is that this neural network also use another feature is called max pooling. So this max pooling is reduce the spatial dimension while keeping all the important information in the similar way. Is just downsample by taking the max value in the window. I'm going to show you an example of that. For example, if this is the image and we are trying to do max pooling, is then we can then this is the max pool size. This is 2x2 window, and within that window we will be looking for the maximum intensity of the pixel, and that will be coming here. And again in this window we'll be taking 30 as the max one. So similarly, from each of this cell we are taking this to reduce the dimensionality, and you can see that the inherent property of the image is still there. And here you can imagine why we are doing max pooling is that image has a lot of redundant pixel. So if you see a large image, so all the nearby pixel will be almost having similar values. So if we downsample it, we can reduce our complexity of the model, and at the same time we can preserve the basic spatial information of the image by doing that. So this is these are the thing for convolution neural network. Here now I'll be defining C for 10 classifier, where I where I am inheriting TF Kera's model by which we'll be getting all the functionalities which we don't have to write, such as compile and fit. All those feature will be getting from this base class. And now I'm defining here our first convolution 2D layer with 32 filters, and this is the filter size, that's 3 by 3, and using the activation function relu here. So here this is the activation function which basically keep all your positive number as it is, and if something is negative and 0, it will make it 0. So this is one activation function which is widely used for convolution neural network. And next, I'm adding another convolution layer. Here the filter size is 64. After that, I'm adding a max pull layer where the size is 2 by 2 grid, as I have shown you in the example. After that, a dropout layer. So the dropout layer is basically dropping out neurons arbitrarily in between, and it will help you the network not to be overfitted. And next, after all those convolution and max pooling operation, basically then these are going to a dense layer, so fully connected layer with 128 neuron. And from that dense layer, one more dropout layer, and finally this dense layer with 10 output neurons. So, and here the activation is softmax. So basically this is the final dense layer which is responsible to give us the classes, and the activation is softmax. That's why, because it's going to give us the probability distribution of each classes. So that is how we defined our model here. Now this is the input to our first layer. Here you can see that it's not flattened like the earlier one, and the output of this is going to be the input of second convolution layer, and the output of this layer is going to be in the pooling layer, and so on and so forth. Now, so we can now we defined our model, and then we can train our model here. So here we are calling our C10 classifier here, and do the compilation using sparse categorical cross entropy. Here using Adam optimizer. And then finally we are fitting the X train and Y train with the batch size mentioned. Yeah, so the batch size is passed from here. Is argument here. So we'll get batch size from here and number of training epochs. And this function will return the history and our model. So let's run. Here again, I define the batch size as 512, and the epoch is 3, and learning rate is 0.01 with those type of parameter. And training the model. The model training might take a few more minutes. Some more. I can see someone raise her hand.
Yeah, Anna, go ahead if you have a question.
Yeah, so if the convolutional filters, you were talking like it pulls out features from the various parts of the image. It's still a black box though. We can't necessarily go back and see what that feature was, right? It's just something that the network has decided is important, but we can't like, I'm just double checking. We still can't go back and be like, this is what that feature is.
Yeah, right. So that's right. The network is deciding what is the important feature. We are not defining that these are the feature and you should use that for classification. So here we are giving that to our model to decide what are the feature is is important to do the classification. But yeah, there are way to visualize what are the feature it learns from the learned weight of the network. But yeah, that's the thing. So we are not deciding what are those features, because yeah, so that is what I was saying, that in computer vision or in early machine learning things, so we used to define that the handcrafted features. So maybe the age feature is important, maybe, but we don't know what is important. That maybe or may not be important for classification, but we are thinking that that's important. So here, instead of deciding by ourselves, the network is learning what is important for classifying those images.
And I just wanted to add, when you inspect those filters, the filters give you a clue as to what the network has learned is important. So in images, for instance, your first layer often learns things like transitions between various colors of pixels. So it learns edges that are horizontal, vertical, diagonal, so that it can map out where things are changing. And then as you get further in, the patterns are, the filters are covering a larger area of your image and can process more complicated features.
Yeah, right. To that point, I just want to mention that filter size, like what we are deciding 3 by 3, is responsible for that, is important, because when we are deciding 3 by 3, instead of that, we can decide 5 by 5 also. But when we are deciding 3 by 3, that is looking at local area. So if we decide to do like 5 by 5, then the area will be larger. So it's gonna be you can imagine like from more local to more global kind of feature is gonna extract based on the size also. Yeah, we finished the training here. So if we visualize the loss, you can see like we just train for very few epochs. You should do that for larger epochs, but for this time being, we are training for just 3 epochs. And here you can see that loss is going down nicely and the accuracy is going up. So here, let's see what is the test accuracy given the model. So here you can see that test accuracy has improved from 40% to 58%. And if you wanna see that how the confusion matrix looks like for this, you can get it from here. So in the ideal case, it should be all diagonal, but the all misclassification are around it. So you can see that and if you see that classification accuracy per class, then you can see that all of this class accuracy has improved, though like the class 2 accuracy is still low, but overall all of the accuracy has improved from the earlier model, which was fully connected. So here we can we should train the model for larger epoch, and that will show you that will show you increase in accuracy. So here that is one example how we can train the CNN using Keras framework. Now here is one example if you wanna check it out, how this training loop is running and how it is taking and how it is using the batch size, taking images in batches and doing the training. For that, here here you can see like we defined the loss function, how is this here we are calculating the loss and returning the loss here, and here is the forward pass function where you can see that we are calling the model and passing the batch size, computing the loss and returning it. And this is basically the training loop, what we have done using what we have done here in the fit function Keras. Here you can break it down. So in that function, if you see that this is the training iteration, is taking the data, true level, model and optimizer, and is calculating the loss and apply the gradient and then returning the loss. And here in this loop, it is basically running the epoch, and here in each epoch is shuffling the data and taking the data in batch, and then for each of these batches is calculating the loss. So let me run this. So here also in the training network definition, I'm calling the classifier, then optimizer as Adam, and then the training loop. And finally here, defining, here is getting the data set and defining the batch size, epoch and learning rate. And after that, I'm calling that function train network with batch size, epoch, and learning, right? So so if you, so this is just and this is just an example, like if you wanna see how this training is happening, and but eventually is the same thing we did using Keras.
Tanwi, while we wait for things to
Yeah.
run, there's a question in Slack.
Sure.
Paul asked, are there filters for edge detection or segmentation, something like that? Is there a good dictionary of filters or selection that can be learned?
And so for age detection, yeah. So basically, I was mentioning that filter size is important because when we are detecting age, we are looking at a very local area in 3x3 grid. So yeah. So if we wanna initially, if we wanna look at the low-level feature like ages, we should use 3x3 filter size.
Paul saying not just the size, but the contents of the filter, contents in the filter.
So contents, so is basically that is getting learned during the training, right? So we are here, if you see here, if you see that we are defining the number of filter and the size of the filter and activation function, and now we now this is our classifier, right? And we are then fitting that classifier with the training data, and in each epoch these filters are basically getting learned by the model, the content of the filter.
Paul says thank you. Well, we're waiting for things. Are there any other questions that folks have? You're welcome to raise your hand or post things in Slack. We have another question. Leo says, can layer-wise relevance propagation, LRP with CNN, be used for determining the most important spatial features in the input?
What is the question here?
Leo, do you want to unmute and maybe ask more?
Oh, what I'm asking, like if we can use some sort of back propagation from the output to actually get a hint of what are the spatial features that are most important that are coming from the input. So if that would be doable in this training that we are doing here in the notebook, or some other method to get to that.
So yeah, so if you want to know what are the features which is used to perform the classification, we can do we can add attention also and see like what are the features which it gave importance while doing the classification. And what you mean by layer-wise propagation, layer-wise relevance propagation?
It's a method I heard about that could be used with convolutional neural network. That's why I was asking about it. So that it can show you the main areas, let's say, and patterns that are coming from the input. They're kind of defining the weights of the network. And
right.
Yeah, but I guess it's
So
not
is it using attention? I think it's using attention, because when you add this attention layer, it will show you like where it is paying more attention for doing the classification in each of this layers. So I think you can
yes.
get a good visualization of like the feature importance
Mhm.
from your network using that.
Okay, thank you. Yeah, I see it's not like a widely used method then, but and then there's someone that posted another possibility on the Slack. I think Bethany just kind of was answering the question. Thank you very much.
Thanks, Ben. Thanks, Leo. Yeah, so so using that network also we finished the training. Yeah, and this is just like the earlier one, is just to explain how we can write the training loop, and we can also understand like what is the facility we are getting from using the Keras interface. Instead of writing all those training loop, we can just use this compile and fit function to get our results. So now for our homework, the thing is that we are interested to improve the accuracy of the model, because there are several hyperparameters I have discussed today, including the batch size, learning rate, epoch, and all those things which are important for training the model. So changing those, how can we increase the accuracy of the model? With that, I'm going to end this tutorial. I'll be happy to take if there is any other question.
Umi?
Hi. So from the first the other in-class worksheets, like the one we did, I tried to like change those parameters, like increase the number of epoch, change the optimization and all like that. But out of the three, it's only the epoch that seems to give me like a change in accuracy. So I understand that machine learning parameters and hyperparameter tuning is task dependent, but what would you say generally about the choice of, parameters when writing a model of machine learning algorithms?
Yeah, so are you talking about the in-class problem, the fully connected network?
Yeah. For the first notebook.
Yeah, so have you tried changing the batch size? Because in that example, the batch size was quite large, and if you reduce the batch size, you can get a good result. So because there we train it for 30 bucks, but the batch size was like 512. So basically when we use very large batch size, it look at the training large chunk of the training data at a time. And that's why it lose the generalization capability on the test data set. So if you try reducing the batch size, it should help you to improve the accuracy.
Thank you.
Any other quick questions? We have about 6 minutes before our hard cutoff. All right. Well, feel free, if things do come up as you continue to work through the notebooks, obviously feel free to put things in Slack, and we'll get to your questions from there. And with that, I want to thank Tanwi for coming and talking to us today, and we'll finish things off. So thank you, everyone. See you next week.